Hello everyone, my name is Chi-Thanh. I'm now a PhD candidate at Civil and Environmental Engineering Department, the University of Alabama in Huntsville. I have been working on the EPA P3 project titled Low-Cost Household Water Filter for PFAS Removal since late 2019. Per and polyfluoroalkyl substances, PFAS, constitute a large group of persistent anthropogenic chemicals that have been widely used for various commercial and industrial products since the 1940s. Because of their chemical and physiological inertness and wide uses in nearly every aspect of our daily life, these chemicals are now ubiquitous in the environment, including drinking water sources. PFAS have drawn much attention in the scientific and regulatory community globally due to their adverse environmental and public health effects such as endocrine disruption and cancers. PFAS are resistant to biodegradation and most thermal and chemical treatment, making them exist everywhere in the environment. Absorption as a simple and economical treatment is considered a good option for PFAS removal. The absorbents commonly used for PFAS removal are granular activated carbon (GAC) and anion exchange resin. However, these absorbents still suffer common limitations like limited capacity or the difficulties in regeneration. In particular, they are not effective for the removal of short-chain PFAS, which have been used as the alternative for long-chain PFAS, but also share the similar environmental concerns. Inspired by the affinity of PFAS for proteins, we aim to develop novel low-cost biohybrid absorbents for point of use (POU) treatment of both long-chain and short-chain PFAS at homes, offices, and thus help promote safe drinking water supply. The research work mostly includes two parts, namely preparation of biohybrid absorbents and PFAS removal experiment. In the first part, protein solution and GAC are mixed with a predetermined ratio for 24 hours. Then centrifuge is used to remove GAC from the solution. Finally, the biohybrid GAC is freeze-dried. In the second part, first, the PFAS solution and the freeze-dried biohybrid GAC are mixed for 24 hours. Then the water samples are taken for LC-MS analysis. So far, we have achieved some promising results. As you can see, the loading of proteins, lysozyme, LYZ, and bovine serum albumin, BSA, generally enhance the PFAS absorption capacity of the substrates, and GAC performed the best among the three substrates. Since GAC has long been used in water treatment and are commercially available, we selected GAC as the substrate in the following study. In addition to BSA and LYZ, we also tested BGG and AAM loaded on GAC. It is worth mentioning that protein functionalization has improved PFAS absorption 3 to 4 times for the challenging short-chain PFAS, demonstrating the great potential of biohybrid absorbents for such applications. So to move on, we will further study the effects of solution chemistry, like pH, ion strength, and coexisting compounds, onto PFAS removal performance of the biohybrid absorbents. Then we will also test the biohybrid absorbents with real tap water. We would like to thank the U.S. Environmental Protection Agency through the EPA P3 grant SU-A3981001 for their financial support.